Hello, I'm Josh Demude. Welcome to the fifth lecture of Unit 3 of CSE 550 on network flows and matchings. In this fifth lecture, we're going to finally actually start looking at algorithms for maximum flow. So up to this point, we've defined both the maximum flow and the minimum cut problems. We've looked at their LP formulations and we've connected them to one another using duality and the max flow min cut theorem. So with all those things in mind, what we can now finally do is actually apply the primal dual algorithm to maximum flow, because we have both the primal and the dual. And we can use that to derive an efficient algorithm for max flow. So first of all, just recall the dual LP that represents maximum flow. There have been no changes here. This is the same as what was in previous lectures. Just as a quick reminder, we're maximizing a variable that represents value. We have flow conservation constraints that correspond to nodes. We have edge capacity constraints that correspond to edges. And then we have our usual non-negativity constraints. Now, when in the primal dual algorithm, and I know it's been a little while since we've talked about that, but in the primal dual algorithm, we eventually need to form DRP, or the dual to the restricted primal. And just as a quick shortcut, I know before we were doing very lengthy kinds of derivations, but as a shortcut, we get DRP from D by replacing all constraint right-hand sides by 0, removing any dual constraints that are not tight. These are the so-called inadmissible columns, if you remember that. And then finally, we upper bound all dual variables by 1. Well, the replacing right-hand sides by 0, that seems easy, and upper bounding all dual variables by 1, that's straightforward. But the only big question here that remains is, which constraints are tight? How do we know? Well, remember, tight is equality. And, well, we have 3 sets of equality constraints right here. With flow conservation, we know this is always equal to 0, so thus these are always tight. We don't need to worry about those. What we do need to worry about are the edge capacity constraints. We don't know right off the bat whether our flow is strictly less than the capacity or whether it's saturating the edge and it's tight. It's exactly equal to the capacity. So here, we need to differentiate. We say that the edge capacity constraints are tight if f of e is equal to c of e. So these are the ones that are tight. The rest of them we can remove. So when we make all these changes, we get the following LP. Let me just quickly walk you through what happened. The right-hand sides of everything are now 0, and we want all of them to be inequality constraints now. That's how the DRP works. So right-hand sides are all 0. We have upper bounded all the variables by 1, and we have only kept the constraints that are tight. Remember, all of our, on the last slide, all of these were tight, so we are keeping all of them here. And the only edge capacity constraints that are tight are those for which f of e is equal to c of e. Okay, so this gives us our DRP. Now, how do we interpret this? Well, if you notice, looking down here at the last 2 rows, we see that f star, which represents the value, is at least 0, but it's at most 1, right? So we know that f star is bounded between 0 and 1. And we also know that f of e is equal to 0 whenever we have this tight constraint. That's exactly what's happening with this constraint here. We know that f of e is non-negative, but it's also at most 0. Combining those 2 things together makes it exactly 0 for all of these tight constraints. Now, if we're trying to maximize f star and we know that it exists between 0 and 1, it's not a bad idea to just like try out f star equals 1. That's clearly the best value we can get. So here's what happens when we plug that in. We're maximizing f star, which we're trying to get equal to 1. And we've replaced f star where it used to be a variable now as 1 in the rest of this. And though it may take a second to sort of stare at and realize, this is basically exactly shortest path. Well, not even shortest path. It's just a path problem now. We want to make sure that when we come in to a node, we also leave it. That's this middle thing here. And also we want to come out of S exactly once, and we want to come into T exactly once. So this is now all about finding an ST path, but there's a catch. We're not allowed to use these tight edges. Why? Because f of e is equal to 0. So somehow we're only allowed to traverse edges E when f of e is strictly less than the capacity. Let's make that more formal with the Ford-Fulkerson algorithm. So you've possibly heard of this algorithm before. It often gets mentioned or at least partially explained in undergraduate theory courses. Really what we're doing here is showing you how it comes from this deeper idea of duality. Anyway, here's how the Ford-Fulkerson algorithm works. It cares very, very much about this central idea of an f-augmenting path. Just like we saw on the last slide, the f-augmenting path, this thing we care about, is an ST path where we're only allowed to use certain edges. What are those edges? Well, we're allowed to traverse edges in the forward direction if they are not tight, okay? If f of e is strictly less than the capacity. This came directly from the primal dual that we derived on the last slide. The f-augmenting path is also going to do something kind of interesting. We're going to allow it to traverse directed edges backwards, only if the flow is positive. Let's look at an example of this. It's been a lot of math, and I think it's time for an example. Let's suppose that we have this example graph and this example flow. Clearly, edge capacities and flow conservation are being satisfied, so we don't need to worry about that. But what is being drawn here in these dotted green arrows is one possible f-augmenting path. Let's take a look at the edges that it's using. So here it's traversing S to A in the forwards direction. Note that it's allowed to do this because 1, the flow value, is strictly less than the capacity, 7. So because 1 is strictly less than 7, it is allowed to use this edge. Secondly, it's using A to C for exactly the same reason. It's forward because 1 is strictly less than 4. And then we get an interesting thing. When we go from C to B, we're actually traversing this edge backwards. We're allowed to traverse it backwards because there is positive flow being sent on the original edge, right? There is one flow being sent on the edge. So we're allowed to walk it backwards. The last two edges, B to E and E to T, are valid because the flow here is 0 and the capacities are strictly larger. So this is an example of an f-augmenting path. Before we talk about the algorithm, let me just say why this is so useful for us. What an f-augmenting path tells us is that we could push some new flow along the edge that we identified, undoing any edges that we do in the backwards direction and adding more flow to any edge that we traverse in the forward direction. And when we do this, we're actually going to get a flow of higher value. This is exactly the idea that the Ford-Fulkerson algorithm exploits in order to get maximum flow. So the input is the same stuff that we've had as always. What we're going to do is we're going to initialize flows f of e equals 0 for all edges. Remember from last lecture that, or 2 lectures ago actually, that this is always feasible. So we're always allowed to start at all zeros. And then the algorithm works as follows. It says, while we can find an f-augmenting path, do this stuff, and this stuff is going to get us a flow of higher value. So we just keep looping through this as long as we can find an f-augmenting path, and we do it, keep continuously improving our flows until there no longer exists one, and then we terminate. So the nuts and bolts of what's actually happening in here. look a little scary in math, but in a couple slides, we'll do an example. So if you're not following this, it's okay, but let me just explain this. So the first thing you do is you find your f augmenting path, which we'll call fancy p, and you compute a value. You look at every edge on the fancy p path that you found, every edge on the f augmenting path, and you find the smallest of the following. If the path traverses an edge forwards, then the value you care about is how much space is left over in that edge. Remember, we only traverse edges forwards when the flow was strictly less than the capacity. So this value tells you sort of how much is left over, how much more we could put through that edge. If we traverse the edge backwards, the value that you care about is how much edge exists on, how much flow exists on that edge. Anyway, you take all these values and you find the smallest possible amount. Then you update the flow values as follows. If you traversed it forwards, you add that amount. So you do more flow in the forwards directions. And you take away that amount of flow if you traversed it in the backwards direction. This is going to make more sense with a picture, but the point is we're basically pushing new flow along our augmenting path, adding where we went forwards, subtracting where we went backwards. Now, the theorem that we have in the proof supplement, the proof is there, we're not going to talk about the proof in this lecture, is that an ST flow is maximum if and only if there is no augmenting path. Clearly, this while loop will terminate when no augmenting path exists anymore, which means that it terminates when the ST flow is maximum. So we show here, or because of this theorem, we know that Ford-Fulkerson solves the maximum flow problem optimally. There's one last thing we need to talk about, a small catch with Ford-Fulkerson, which is, what is its running time? Do we know that it terminates? We know that if it terminates at a maximum flow because of this theorem, but are we sure that it ever terminates in the first place? Well, there is a thing that's in the textbook, which we're not going to talk about in detail here, but the observation is if the edge capacities are integral, so notice we've actually changed this. It used to be for real values. Now we're talking about positive integers. Then what you know is that every augmentation, meaning every loop in Ford-Fulkerson, it increases the flow by at least 1. So it steps up by 1 and by 1 and by 1. Because there are only a finite number of f augmenting paths in the graph, and we're increasing the value 1 by 1 by 1, we know that we're on a steady march towards the optimal, and eventually we will terminate after a finite number of augmentations. Interestingly, this is not true if we allow these capacities to be real. In the original Ford-Fulkerson paper, they actually showed that if you set up the edge capacities in a particularly nasty way, using irrational capacities, you can trick the Ford-Fulkerson algorithm into never terminating. So that's why usually when people teach Ford-Fulkerson and talk about it, we talk about it only in the case where there are integral capacities. The other side note of this is that there is no nice, big O of n or big O of n squared kind of running time. All we know about Ford-Fulkerson in this case is that it terminates in a finite number of augmentations, which is why we often talk about Edmonds-Karp back-to-back with Ford-Fulkerson. The Edmonds-Karp algorithm for max flow is identical to Ford-Fulkerson, except for it adds this one word to the description. It says, while there is a shortest f augmenting path, do this stuff. So it's identical, but instead of considering any augmenting path, as in Ford-Fulkerson, here we look for shortest f augmenting paths, and we can do this very easily with something like breadth first search starting at S. We just need a shortest ST path that is f augmenting. The runtime theorem for Edmonds-Karp is that it only uses the number of nodes times the number of edges over 2 augmentations. Each augmentation takes a certain amount of time, and therefore we can get a nice polynomial running time for Edmonds-Karp. We're going to conclude this lecture with a actual example of this. I will just warn you ahead of time that this is sort of visually very messy. There's a lot of different things we need to keep track of. So we're starting very simple. As always, we have our nodes, specifically our source S and our sink T. The numbers here are the edge capacities. And I want to say upfront that I am only going to draw flows if they have a positive value. Any zero flow values, we're just going to omit for visual clarity. Initially, the Edmonds-Karp algorithm initializes zero flow everywhere, so there's nothing to really worry about here. Then we enter into the while loop. We're looking for a shortest F augmenting path. So it's useful to understand what edges we're actually allowed to use in order to be F augmenting. Remember that there are two kinds of edges we're allowed to use. We're allowed to go forwards if the flow value is strictly less than the capacity. We're allowed to go backwards if there is positive flow. Well, right now there is no flow anywhere. So we're allowed to go forwards on any edge, right? Because zero is strictly less than any of these capacities. So we're allowed to go forwards everywhere. If we run breadth first search on these purple edges, what we'll find is that the shortest path is this one highlighted in green. And because we've restricted it to only the edges that an F augmenting path is allowed to use, then of course, now this is a shortest F augmenting path. What's the next step? Well, we need to figure out this gamma value, how much we can augment it by. This is the minimum of the following. So notice these are all forward edges. So here we're comparing 7 minus 0 flow to 4 minus 0 flow to 2 minus 0 flow. The smallest over all of these things is 2. Now that's very mathematical, and that's how we figure out that gamma is 2. But I want to give you a conceptual understanding. The idea is we want to push as much flow as possible on this F augmenting path that we found, but we have to do it while respecting both non-negativity and edge capacities. Clearly, if we tried to push 7 flow on this path, we'd be in trouble, right? We could get 7 flow from S to A, but then we have nowhere to put it because the resulting edges after that, the subsequent edges, they can hold less. So what we're trying to do is push as much as possible while still getting it through. And of course, here the bottleneck is 2, right? 7 can hold 2, 4 can hold 2, and 2 will be fully saturated by 2. So augmenting F by this 2 flow that we're going to push through, we end up with an updated flow that looks like this. We're pushing 2 all the way through. All right, but now that we have a flow, the edges we're allowed to use are different. So everything that's not next to a blue arrow is the same as it was before, but we need to look at what's going on with the blue arrows now. Now there is positive flow happening on all 3 of these edges, which means we are allowed to traverse any of them backwards now. So you'll notice that there are backwards directions in the purple arrows for all 3 of these flow edges. However, we're also allowed to traverse some of them forwards. Remember, we're allowed to go forwards anytime there's some room left over. So here with 2 flow and 7 capacity, there's 5 flow left over. There's some room. Same deal with 4 and 2. There's still some room, but there is no room left over in this last edge, right? We have sent 2 flow, and that is the full capacity. So there's no room left over here, so we can only traverse that edge backwards. All right, well, this is easy enough. Once again, we're going to run BFS on the purple edges, and now we're being shown that this green path is our shortest F augmenting path. And this path, once again, we need to find the bottleneck. Well, there's 5 room left over from S to A, there's 5 room left over from A to D, and there's 8 room left over from D to T. So here, of course, the most we can do is push an additional 5 units of flow. And when we do this, we increase 2 flow to 7, that's an additional 5. We get 5 new flow going from A to D and 5 new flow going from D to T. So this is now our updated flow. All right, we keep doing iterations. We're going to keep repeating this while a shortest F augmenting path exists. So once again, we look at all of the edges that have flow on them. We're always allowed to go backwards on those. We need to figure out which ones we can also go forwards. But notice now that the 7 edge is fully saturated. There's no room left, so we can only do that one backwards. A to D is also fully saturated, so we can only do that one backwards. The only one that we're still allowed to go forwards on are A to C, which has 2 room left over, and D to T, which has 3 room left over. All the other purple edges are as they have been leading up to this point. If we run BFS on this graph, we get this bottom kind of path here, being our shortest ST path. So this becomes our F augmenting path. And when we ask what the bottleneck is here, hopefully it's very clear without me having to say everything at this point, that this last edge, E to T with 2 capacity, is going to be the bottleneck. So that's going to be the maximum amount we can augment by. When we do so, of course, now this is just 2 flow, flowing here along the bottom. It doesn't affect anything else. Okay, this is where it starts to get very visually overstimulating. There's a lot of arrows happening here. But once again, using the same rules as before, we can determine what edges are allowed by an F augmenting path. Essentially, it just is a backwards edge on this last one that we added because it's fully saturated. Everyone else can go backwards and forwards. And when we run BFS on this graph, we get this sort of non-intuitive path, but it's kind of fun. It goes along the bottom. It passes by this fully saturated edge. Instead, it uses this E to D edge to get around. And then it uses this leftover flow that's possible from D to T to finally reach T. In this F augmenting path, it takes a little bit more thinking to figure out what the maximum amount is we could push through. So let's just quickly look at that. There's 3 room left over from S to B. There's 1 room left over from B to E. There's 10 from E to D, and there's 3 from D to T. So here, obviously, the bottleneck is this B to E edge. It only has room for 1 more flow that it can push through. So it's going to go ahead and do that, passing through 1 extra flow on all of those edges. Finally, we reach the end. So here, one last time, we try to use breadth first search using the purple edges to see if there's any ST path left over, if we can find any more F augmenting paths, but BFS cannot do so. There are no ST paths using only the purple edges. At this point, the Edmonds-Karp algorithm terminates, and we are left with this final optimal flow, which you may recognize from several lectures ago. I told you was the optimal flow. It has value 10, and lo and behold, Edmonds-Karp has found it for us. So this concludes the part of Unit 3 about maximum flows. When we pick back up in the next lecture, we'll be looking at a new problem called a minimum cost flow, which is going to generalize a maximum flow and consider more possibilities.